recording. Okay, so I'm still figuring out what we're dealing with. I understand what IO and file descriptor kind of does based on the usage of it, but here in the Xv6, I don't know if you're creating a new ones or using the existing ones to um, create more sophisticated features. Let's see. I, by the way, got into the this website, ziainp.gitbook.io. Looks like it created something out of from github.com. But this is a useful note. Maybe useful is an understatement. But I got help from. I'm trying to get help for understanding the textbook, the booklet that the lab suggests to read, um, and got this summary of notes. So let's see, let's read and find out what if you can get close to the Xv6 OS development. Okay, so fd is a small integer representing a kernel managed object that a process may read or write. Process obtains the fd by opening a file, directory, device, pipe, or socket. A Unix subfile has different types than what it currently represents. Every process has a private space of file descriptor starting at 0. Xv6 kernel uses fd as an index into a per process table. By convention, fd1 is a standard input, fd2 is standard output, fd3 is a standard error. Xv6 shell ensures the 3 fds are open when starting up. Okay. Read and write system calls advance the file by offset. So next time the read or write starts from the new offset. One interesting aspect is program like cat does not know whether it is reading from file, console, socket, or pipe. Does not know whether it is printing to a console or a file. The use of FDs and the conventions allows some simple implementation of user programs. Close releases FD, making it free for reuse. Usually reallocated FD is always the lowest number unused descriptor of the current process. Unix shell utilizes this feature with fork to implement smart IO redirection and implement pipe. Fork copies parents' file descriptor tables with its memory. The system call exec replaces the calling process. Okay, so I have a strong feeling that I need to utilize some kind of existing repo that houses this code. So when we emulate it in Chimu, it works, as opposed to the function exec, for example, not working here. So let's go to the Xv6 directories. Oh, where was I? Xv6 with me. FCNTL. Okay. So pretty long. Let's see if we can utilize it, right? Utilize it in the Chimu. Is it pipe failed? Okay. Let's see if we can use pipeline keyword like the straight bar. Okay. Pipe. Is there a pipe here? Need kill ln ls make dir rm. Is there a vim here? Oh, this is really lightweight. Not even any text editor. Okay, that's good. Clear? Is there clear? No. Okay. There's something about this that keep telling us that something failed. Can we take a look at it? Let's see. Does not know whether it is reading from file, console, or socket, or pipe. Does not know whether it is printing to a console or a file. Oh, okay. 4 copies parents file descriptor tables with its memory. The system call exe replaces the calling process memory but preserves its file table. So it's just some kind of recursion, you can say. Yeah, for some one of those children's. What's a fork one? PID fork, -1, turn PID. Oh, it's just a forking. What's a panic? Never mind. Some sort of panic function is also defined. Okay. Mm-hmm. Cat. Mm. This is a bug. Okay. Obviously, this operating system cannot avoid bugs either. Mm. Is it worth pursuing? I have no idea. But oh shit. Terminate it. Let's terminate it. 4 copies of the table, but a file offset is shared. The underlying file offset is shared between parent and child. If fork is equal to 0, I forgot what it means to be of fork being 0. That's to dismend fork. Fork creates a new process by duplicating the calling process. The new process is referred to as the child. The calling process is referred to as parent. The child process is an exact duplicate of the parent. The child has its own unique process ID. The child's parent process ID is the same as the parent process ID. Child's parent process, same as the parent's process ID. The child does not inherit its parent's memory logs, process resource utilizations, and CPU time counters. The child's set of pending signals is initially empty. The child does not inherit semaphore adjustments from its parent. Okay. Let's see if there's a return. Okay. On success, the PID of the child process is returned in the parent, and 0 is returned in the child. Oh, okay. That means the fork is successful. Okay. Right. Hello. This is a different value, right? This is a different value. And failure. Okay. I'm an idiot. Let's see. Fork equals 0. Is this a child or parent? When the fork system call returns 0, it indicates they're in the child process. Child returns the positive process ID of the child. Oh, okay. Okay. The child process can execute the code below, and then the parent can be executing the else. Okay. You know what the file offset is shared? FTP is basically an index pointing to an actual file object. The file is shared between parent and child. To fork and duplicate, the reference count of the file is incremented. Else existing file, non-existing file. It tells the shell to give the command the file descriptor 2 that is a duplicate of descriptor 1. Both the name of the existing file and the error message for the non-existing file will show up in the file type 1. Really? Okay. Let's do Chimo again. Alright, so um ls. How do I create a file? How do I create a file? Echo hello world. Um cat read me. As a teaching operating system for, so we're more interested in simplifications and clarifications than new features. You'll need a risk-free new lib toolchain from and compile for risk-free 64 soft MMU. Once they're installed and in your shell search path, you can run make gmu. Put your code in user sleep.c. Okay. Um, okay. So the user arguments are written in this way. For echo, it is just using a write function. Where is this write function coming from? Oh, either the types H or user H. Okay, see if there's a tag. Let's see. Oh, there's no tag. Okay. Let's see. Let's go to user H. There's some ASM file. Right. Wow. This is a lot. This is a lot! But it's okay. Let's not be afraid. I just almost failed my course. This is very interesting. So even the printf is already defined. Printf C. Wow. So they did write everything here. That is super interesting. Sleep C. Well, the sleep C shouldn't be here. Let's see if it can. How to execute terminal command. Okay. Stat user.h. Let's go to user.h. Is there a right call? Malloc for exit wait pipe right. Yeah, there is wait. Stat. Okay. System calls. can't find it. Okay, current. Interesting. It says a sys prefixed with sys instead of just a right. Then how do they call right to actually call the sys right? That's the question I have. Hmm. Okie dokie. So I think this process is um, of what we're doing is we're implementing on top of what we have in the Xv6 kernel to create an operating system uh, on top of the kernel that's right existing here. Okay, Unix is a combination of standard file descriptors, pipes, and convenient shell syntax for operations on them was a major advance in writing general-purpose reusable programs. The idea sparked a culture of software tools that was responsible for much of Unix's power and popularity. The shell was the first so-called scripting language. The Unix system call interface persists today in systems like BSD, Linux, and Mac OS. The Unix system call interface has been standardized through the Portable Operating System Interface Standard. Xv6 is not POSIX compliant. It is missing many system calls, and many of the system calls it does provide far from the standard. Our main goals for Xv6 are simplicity and clarity while providing a simple Unix-like system call interface. Several people have extended Xv6 with a few more system calls and simple C library in order to run basic Unix programs. Modern kernels, however, provide many more system calls and many more kinds of kernel services than Xv6. For example, they support networking, windowing systems, user-level threads, drivers for many devices, and so on. Modern kernels evolve continuously and rapidly and offer many features beyond POSIX. Unix unified access to multiple types of resources with a single set of file name and file descriptor interfaces. This idea can be extended to more kinds of resources. A good example is Plan 9, which applied the resources are files concept to networks, graphics, and more. However, most Unix-derived operating systems have not followed this route. The file system and file descriptors have been powerful abstractions. Even so, there are other models for operating system interfaces. Multics, a predecessor of Unix, abstracted file storage in a way that made it look like memory, producing a very different flavor of interface. The complexity of the Multics design had a direct influence on the designers of Unix, who aimed to build something simpler. Xv6 does not provide a notion of users or of protecting one user from another. In Unix terms, all Xv6 processes run as root. This book examines how Xv6 implements this Unix-like interface, but the ideas and concepts apply to more than just Unix. Any operating system must multiplex processes onto the underlying hardware, isolate processes from each other, and provide mechanisms for controlled interprocess communication. After studying Xv6, you should be able to look at other, more complex operating systems and see the concept underlying Xv6 in those systems as well. Okay, write a program that uses Unix system calls to ping-pong a byte between two processes over a pair of pipes, one for each direction. Measure the program's performance in exchanges per second. Oh, wow. This seems tough. This looks tough. Okay, let's get into it in the next session.